In this last video, we're going to talk about using calculators to evaluate logarithms. In my opinion, this is the easiest section of the semester, of the entire class, by a long shot. The reason why is because you're using calculators to do most anything. You just have to make sure you understand how to use the calculator. And that can actually be kind of a chore for some calculators, because some can be kind of difficult to use. That's why I recommended at the beginning of the semester the specific TI calculator that is very easy and straightforward to use, very easy to use fractions with it. And we're going to be using fractions in this section. Now, the fact that this is the easiest section of the semester comes with one caveat. You have to have a scientific calculator. It can't be a four-function calculator. It has to be a scientific or a graphing calculator. A graphing calculator doubles as a scientific calculator. It must have a log and a natural log key. So, like this one right here. This is my on-screen scientific calculator. It has the log and natural log keys. You can get these for a handheld one for $10 at Walmart or Target, or in the campus bookstore. I don't know what the price is there, but you'll probably get a better price at Walmart or Target. And remember, these calculators cannot be phones or PDAs or tablet computers or laptop computers. If it has a QWERTY keyboard or a touchscreen, it's not a scientific calculator. It's a computer, so that's not something that you can use in the class. And you know, it's only $10 and it's a good investment. You'll probably be using it in the next class. Some professors will only allow non-graphing calculators, so you know, $10 might end up going a long way. TI-83s and TI-84s are allowed in this class, but some kinds of calculators that are not allowed are TI-89s, TI-92s, and Voyage 200s. Those are not allowed, and to tell you the truth, they're kind of difficult to use anyway. So you would probably want to, if you want to invest in a graphing calculator, and that's a good investment too, you'd want a TI-83 or a TI-84, probably TI-83 just because it's cheaper. The reason why I'm not quick to suggest getting a graphing calculator is just because they're expensive. You know, they cost a good deal of money. So let's go ahead, and now that we have that disclaimer out of the way, let's go ahead and get started with this actual section. Now, the main thing here is that we need to know that a scientific calculator can approximate common logs and natural logs. So, let's say, for example, let's get this out of the way just for now. We'll bring it back in just a second. If we have log of 10. Well, remember what log of 10 means. That means if it just says log, that means it's common log, so it's base 10. So we can kind of see, I mean, just by hand, we could see that, okay, this is the solution of 10 to the power of x equals 10. So that means x is going to equal 1. Well, let's do that using this calculator. So we have try to get that so that's not so much in the way. So we have, oh, now I lost track of the, let's go ahead and get that out of the way. We know that x is equal to 1. So we can do log of 10. We probably need to put the parentheses in. Most calculators will put the parentheses in for you. Equals 1. Log base 10 equals 1. Let's scroll a little bit to the right. So log base 10 equals 1. Let's do log base 100. Not base, excuse me. I said base a second ago too. I mean common log of 100. So log of 100. Let's see if this works without parentheses. Ah, it does. 2. So log of 100 equals 2. Let's go even more to the right so we can see it more clearly. Now let's do something a little bit strange. See, log of 25. See, log of 25 is something that we have not been able to do before because this is something that's going to require a calculator. It's, very strange. We could do log base 5 of 25. That'd be easy. That's 2. But what power of 10? 10 to what power is going to give us 25? Okay, well, we'd have to use a calculator to figure that out. So it's going to end up being 1.39794 blah 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 blah. So I'll write this down as 1.39799, and I'm going to stop there. The reason why is just because I don't know why, but I always thought that the standard place to cut off if you don't know how many significant digits you need is 4. So after 4 decimal places, that's where I stop. So log base 25, previously we couldn't do that at all, is 1.39. About. I'm going to change that equals to about because that's not an exact number. And I'll put a dot 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 there. That's going to be an irrational number, I assume. I can't imagine what rational number would give that. Now let's do one more. What is log of 1? Okay, so log of 1 equals 0. And that makes sense, because this means 10 to what power equals 1. Well, anything to the power of 0 equals 1. So it makes sense that log of 1 will equal 0. In fact, it doesn't matter what the base is. This could be log base 4, log base e, log base pi. It's still going to be 0. If you take the log of any base of 1, it's going to equal 0. Just like anytime you take any power to 0, it'll give you 1. So now let's do a couple more examples. Let's do, instead of common log, let's do natural log. Let's do natural log of e. Let's scroll down. Natural log of e, well, this should be simple enough. Natural log of e equals 1. Natural log of e equals 1. Oh, that makes sense, because e to the power of 1 is going to be e. This just means what's the solution of e to the x equals e? Well, x is going to equal 1, which is why we have 1. So now let's do natural log of 1. Natural log of 1. I did something wrong, but I'm not sure what it was. Ah, I see. Okay, so natural log of 1 equals 0, and that, again, makes sense. It's just like what we had up before. We had common log of 1 equals 0. So natural log of 1 also equals 0, because e to the power of 0 will give you 1. Now let's do natural log of, and this is going to be kind of strange, 7.3890462. 7.3890462. So natural log of 7.3890462 equals pretty close to 2. In fact, I'm going to go ahead and approximate that and say it's about 2. And why is that about 2? Well, let's take e to the power of 2. E to the power of 2. Well, that's 7.38905,609, and that's, you can kind of guess that's where I got it. Now, my calculator that I had with me whenever I wrote that out gave me a slightly different answer, but bottom line is it gives us pretty close to 2. Okay, now I have one quick note. Let's get this out of the way for this quick note. the book makes mention of something called an anti-log. Now, I must admit, in my entire life, I've done a lot of math. I have never seen anti-log before. But what they have is that anti-log of x is going to be equal to 10 to the power of x. That's the definition of anti-log. It's just the inverse of log, and since log is inverse of 10 to the x, that means anti-log is just going to be 10 to the x. I don't know exactly why they felt the need to do that. That seems a little strange to me. But just so you know, there's exactly one problem in the homework that involves anti-log. So there it is, so you don't get confused. Anti-log is just the same thing as t to the power of x. So don't let that throw you off. It's very strange, but there it is. At least it's simple. You know, it's strange, but it's not hard to get around once you know what anti-log actually is. Now let's do this example. This example it's going to be something that involves the calculator again, but it's going to be not quite exactly the same thing. So let's have an example where we need to solve log of x equals 1.2794. And so now we get thrown off because we've been punching things into our calculator and think, wait a minute, this is not something that we've been doing before. So what we need to do is we need to think, okay, what does this mean? This means, so we have log base 10, we can put this in an exponential form. So we have from 10 to here, so we have same base, 10 to the power of 1.2794 equals x. Okay, well now that's easy enough. We can punch that into our calculator. So I'm going to go ahead and write that down just so we have that. 1.2794 equals x. Oh, whoops. I had a similar problem in the previous video. 1 to the power of 1.2794 equals x. So now, well, that we can punch into the calculator pretty easily. So we have 10 to the power of 1.2794, close parentheses, and enter. And it comes out as 19.0283, about. So we'll say that x is about 19.0283. So that solves that. It was simple enough. It's just whenever you are punching things into the calculator and you're not really thinking about exactly what you're doing after so many problems, you think, wait a minute, this is not what I thought it was. Okay, so that concludes these just straightforward punching into the calculator, but there's still one more thing, and this is very important. This one is the more difficult part of this section, but once you understand it, it's not difficult at all. It's called change of base formula. It's a very basic, very important property of logarithms. So you may have noticed that all our calculators, they can do common log and natural log, but you know, what about log of 4? What about log of 5? What about log of 2? Well, the change of base formula takes care of that for us. The change of base formula says that log base A of B equals log base C of B over log base C of A. And C can be any positive number. Really, A and B are both positive numbers too. But the basic idea of this is we can write this log as the what's the word I'm looking for? The quotient, the dividend, whatever, I don't know. We can write it as a fraction, that's probably the best word, a fraction of two different logs. Any log that we have, we can write as a fraction of two other completely different logs. So as long as we have the same base on top that we have on the bottom. In this case, it's going to be C. It needs to be C everywhere else, too. So that means if we have, I'm going to write this out here, log base 2 of 5, well, we can't compute that by hand. I mean, that's really bizarre. What on earth, what power of 2 is going to give you 5? Well, whatever it is, our calculator, it doesn't have a log base 2 anywhere, so we can rewrite this as log of 5 over log of 2. And I'm using common log here. It doesn't really matter. I could make this log base 5 over log base 5, but what would be the point of 5? Because we want this to be something that we can use in our calculator. So just to finish this up, let's go ahead and rewrite this. This is going to be log of 5 over log of 2. So log of 5 over log of 2 equals 2.321 blah blah blah. So let's make that an approximation actually. 2.3219, and let's test that. Let's do 2 to the power of 2.3219. So 2 to the power of, I keep forgetting where the power key is, 2.3219 is equal to pretty close to 5. Now remember that this was an approximation. I didn't write out the complete thing. And same thing here. This is going to be, it's pretty close to 5. It's not exactly 5 because I didn't write down every single little thing here. So that's an example of using the change of base formula. And we again, it can be common log, it can be natural log. Natural log is generally preferred because it's more standard. Like computer programs would be more likely to use natural log. The back of the book would be more likely to use natural log. Although in this particular homework section, it has a section where you use common log and a section where you use natural log, but it really doesn't matter. I didn't close the parentheses here. That's going to drive me crazy. Okay, close parentheses. So natural log is generally preferred, but it really does not matter. You use either one and it is fine. So now, like I showed up here, we can calculate logs of any base using our calculators. Let's do one that's pretty simple. I mean, we already did an example that's kind of complicated, but let's do something that's just to show that it works. Let's do log base 5 of 25. Oh, I need to scroll down. Log base 5 of 25. Well, that's going to be equal to log of 25 over log of 5. And a good way to remember this is that, at least in my opinion, is 25 is higher up, so 25 is going to be in the numerator. 5 is lower, so 5 is going to be in the denominator. So if it's higher up, because I mean this is a subscript, so if this is higher up, so it's going to be in the top. That's just the way I always remembered it. So now we can't do log base 5 of 25. Now we know that this is going to be 2 because 5 squared is 25, but just so we can test this new concept, let's try it out. So we have log base 25, but I'm going to go ahead, I'm going to change this to natural log. It really doesn't matter which one, but just so that I can mix it up a little bit, I'm going to change it to natural log. It has to be the same base on top and bottom, remember that. It can't be log here and natural, it can't be common log here and natural log here. It has to be one or the other. So natural log of 25 over natural log of 5 will give us 2. It gives us exactly 2. So 2. And it's exactly what we were expecting because 5 to the power 5 squared will give us 25. Now let's do again another example that is going to have this one's not going to have an obvious answer. And that's what this is for. That's what this is useful for. It was whenever we don't have an obvious answer. So we have log base 5 of 17. Okay, well, that is going to be is going to be log base 17 over log, not base, I just said base when I didn't mean to, log of 17 over log of 5, and I don't want to rewrite that, so I'm going to go ahead and just use common log. I meant to use natural log, but again, it doesn't really matter, just as long as it's the same on the top as it is on the bottom. So natural log of 17, oh, just so you know, most calculators, in fact I'm going to go ahead and do it for this one, most calculators will open parentheses here, and if they do, you want to make sure you close parentheses, especially on the TIs. So if you have log and it says open parentheses 17, if you don't close that parentheses, it will give you something completely different. It'll think that you have the logarithm inside a logarithm, and that's not what you want. So just remember, it's always a good habit whenever it has an open parentheses, you want to make sure it's closed at the right place. So this is the way you would write it almost exactly on a TI calculator. It's going to have open parentheses automatically, and you want to close it before you go to the next logarithm. Because if you don't have that closed parentheses, if you have it written out like this, what this means is log, I'm glad I just thought of this because it's kind of important. This is going to say log of 17 over log of 5. That is complete nonsense, and your calculator is going to spew out something really weird. In fact, let's see what it shoots out. It'll give us 1.388 blah blah blah. But now let's do the correct answer and see how it comes out. So log of 17, oops, 17 over log of 5. So the correct answer is 1.76. So keep that in mind. One of the hardest parts of these classes is understanding how to use the calculators. But if you do know how to work with it, then it can be so useful. So let's go ahead and write down that answer then. This is equal to 1.76037. Alright, now that's the end of this video, and I'm going to have to end it because I feel a sneeze coming on, and that's probably a good way to end the semester. I will see you in class.